Professor Ken Sims from the Department of Geology and Geophysics at the University of Wyoming has succeeded in becoming a National Geographic Explorer who has conducted research in some of the most extreme locations in the world, from volcanic lava lakes to the depths of the seabed.
In recent years, Professor Ken Sims has put his most intense focus on a wonder of the world, the amazing hydrothermal system of Yellowstone National Park in Wyoming. As UW's representative at the U.S. Geological Survey's Yellowstone Volcano's Observatory, Professor Ken Sims has led a comprehensive multidisciplinary research program studying Yellowstone's network of 10,000 springs, geysers, fumaroles, and mud pots.
In addition to creating a more complete picture of the piping in the largest, most immersive, and visually stunning example of an active continental hydrothermal system, aimed to improve our understanding of how subsurface geological processes influence what they call rock-supported life. Professor Ken Sims has dubbed this field of research geohydrobiology. Geo means earth, hydro means water, and bio means life.
Yellowstone geohydrobiology research will provide a better understanding not only of the geology and fluids of the hydrothermal system, but also how those fluids impact the diverse microorganisms that give Yellowstone's thermal features their spectacular shapes and colors, says Professor Ken Sims.
Yellowstone is where earth, water, and life meet in unusual and wondrous ways, and is a natural laboratory for studying these relationships. Essentially, geological processes allow for the existence of rock-powered or chemotrophic life, and in turn, chemotrophic life influences Yellowstone's fluid chemistry, and even the evolution of its landscape.
Besides that, the same processes have been going on since the beginning of Earth's history, and in fact, it is likely that life on Earth originated in hydrothermal systems, such as the Yellowstone system. Yellowstone's surface hydrothermal features are associated with reservoirs deep underground that are heated by volcanic activity and recharged by rain and meltwater from high altitudes.
This fluid descends into the earth, becomes very hot, and absorbs new chemicals, such as chloride and sulfur, from volcanic gases. The chemically enriched hot water then rises back to the surface and forms Yellowstone's iconic thermal features.
As it rises to the surface, the very hot water will boil as the pressure decreases. This boiling results in what is known as phase separation, i.e., the vapor and liquid separate and migrate to the surface via different pathways. Just like boiling a kettle, water is divided into two phases: hot liquid water and water vapor/steam.
However, in Yellowstone, the hydrothermal fluids that emerge from within are more complex and carry chloride and sulfur compounds. When this hot Yellowstone fluid rises from within and boils, a liquid phase with a neutral to alkaline pH, or hydrogen potential, retains most of the chloride.
In contrast, the complementary vapor phase contains sulfur compounds that remain in the vapor. Then, when this sulfur-rich water vapor mixes with oxidized shallow groundwater, a series of chemical reactions occur. Importantly, this chemical reaction involves sulfur metabolizing bacteria, which ultimately make some of Yellowstone's hot springs acidic.
This phase separation process is what gives Yellowstone waters their extraordinary bimodal pH distribution. Of course, nothing is simple, as this phase-separated water and steam may haze with cooler groundwater and surface water as it rises, further influencing its composition.
This phenomenon not only explains the bimodal distribution of water pH, but also helps explain the amazing diversity of Yellowstone hydrothermal fluids, with temperatures reaching nearly 200 degrees Fahrenheit, the boiling temperature of water at Yellowstone's elevation.
Although phase separation can explain most of the chemical variations seen in Yellowstone hydrothermal fluids, our understanding of this important process is greatly limited by our lack of knowledge of the shallow pipes of Yellowstone's hydrothermal features and the time scale on which phase separation occurs.
In essence, we already have a two-dimensional understanding of a four-dimensional problem. We know the surface geometry, water chemistry, heat flow, and microbiology for many thermal features, but we do not understand the final composition of deep hydrothermal reservoirs. We also don't know the time and path of the rise of fluid coming from within.
Geophysical equipment is used such as electromagnetics, ground-penetrating radar, nuclear magnetic resonance, and seismic refraction to obtain images of subsurface pipes of hydrothermal features. Measures the chemical properties of liquid radioactive isotopes that change composition over time.